we have reached quite an important point in our presentation series. Thus far, we have invested significant resources and effort into developing principles of space-time engineering, which describes fundamental particles in terms of the quantum vacuum. However, now is the time for change. We're going to shift focus from particle physics to cosmology, whilst reusing as many of our particle physics derivations as possible. But how are we going to achieve this? What is the missing link? Black holes. Let's see how black holes are the missing link between today and the instant of the Big Bang. We'll begin by describing the universe we see today. This illustration of the universe is actually a sphere represented in 2 dimensions. That is, a circle. Let's now draw a cube around the sphere. The length of the cube is termed the fundamental wavelength. Associated with that cubic fundamental wavelength is its cubic fundamental frequency. As you can see, the fundamental frequency is the lowest frequency solution which fits inside the cube. Obviously, many higher frequencies will also fit inside the cube. This is the origin of the term cubic frequency distribution, which is associated with the quantum vacuum in terms of its innate fluctuations, which should not be confused with cosmic microwave background radiation. These 2 things are very different. Cosmic microwave background radiation sits on top of the quantum vacuum ground state. That is, it sits on top of the zero-point field. In other words, cosmic microwave background radiation simply passes through the quantum vacuum, it is not the defining nature of it. Let's now imagine that we can turn back the cosmological clock. If we can run the clock backwards far enough, the many frequencies of quantum vacuum fluctuations we know today must have originated as a single very high frequency. That is, a single harmonic mode. When we execute this step, we unmask an astonishing result. We find that the dimensions of the primordial sphere coincide with the standard model of particle physics' theoretical limit of physical scale. That is, the Planck scale. The reason that this is so significant is because the only physical object in the known universe to theoretically exist at the Planck scale is the singularity radius at the heart of each black hole. Therefore, in order for the standard model of particle physics to remain self-consistent, it must recognize the possibility of our universe existing as either a black hole, or potentially a white hole. In either scenario, the fundamental wavelength illustrated must be proportional to the Schwarzschild radius. Why this radius? Because the universe has no net charge and no net direction of rotation. Therefore, if our universe is a black hole, it can only be one involving the Schwarzschild solution. So, the missing link between today and the Big Bang are black holes. Let's now take a look at the mathematical model. Our first objective is to calculate the required dimensions of the primordial sphere discussed on the preceding slide. The process to achieve this is remarkably simple. In fact, the hard work was already completed in episodes 5 and 8. By utilizing the simplified harmonic cutoff mode, and the harmonic representation of fundamental particles, we're able to scale from the Big Bang to the current epoch by utilizing the primordial sphere as our reference particle. Hence, our objective reduces to a simple matter of algebraic substitutions. Verifying that the harmonic cutoff mode equals unity at the Planck scale. Now that we have the physical dimensions of our primordial sphere, we can achieve our second objective. That is, to calculate the Big Bang Hubble constant. Once again, the actual mathematical process to obtain our goal is exceedingly simple. As before, it is a simple case of algebraic substitutions. However, in this case, we need to realize that the critical cosmological density at the instant of the Big Bang must have equaled the mass density of our primordial sphere. We know this must be factually correct because the universe has been experimentally verified as possessing flat space-time curvature. This means that, at the very least, the mass density at the instant of the Big Bang must have been extremely close to the critical cosmological density, if not exactly equal to it. The next thing we're going to look at is the Big Bang singularity radius. Before we execute the procedure to calculate the Big Bang singularity radius, we'll execute a quick distraction. What you're seeing now is the determination of the harmonic cutoff frequency of the primordial sphere we described on an earlier slide. We'll pull everything together on the next slide, but for now, I would like to draw your attention to the result. That is, approximately 1/4 of the Planck frequency. This is significant because it does not exceed the theoretical maximum. That is, the Planck frequency. Let's now calculate the Big Bang singularity radius. We shall start by utilizing a 2020 publication by Story, whereby the author accurately calculates an experimentally verified value of the Hubble constant, as measured via the cosmological power spectrum. This information is transformed into the Big Bang singularity radius in accordance with the extremely simple substitution process shown. The result obtained indicates that the Big Bang singularity radius, that is, the size of the universe at the instant of the Big Bang, was approximately 4 times the classical electron radius. For more information regarding the Big Bang singularity in relation to cosmological inflation, please visit the links appearing on screen. Let's now pull everything together. In this episode, we have determined important physical properties at the instant of the Big Bang. From this, we determine how far these physical properties extend, resulting in cosmological size at the instant of the Big Bang. Obviously, the physical properties displayed on screen are important, but what is equally important is to appreciate the difference between our primordial sphere concept and the physical size of the universe at the instant of the Big Bang. We call this size the singularity radius. Our primordial sphere calculations are based upon the condition of maximum permissible mass density, which occurs at the Planck scale. However, since the Planck scale, as classically derived, does not include an experimental relationship function, it is non-physical. Please refer to Episode 1 and Episode 6 for more information regarding experimental relationship functions. To circumvent this impasse, and to calculate a temporary experimental relationship function, we developed the primordial sphere methodology. This means that we are able to calculate the physical properties shown for a Planck-sized particle. However, because the universe was homogeneous at the Big Bang, the properties shown were everywhere. Our singularity radius determines the size of space-time, in which these properties were homogeneously distributed. For viewers wishing to consult literature relevant to this episode, you may do so by accessing the links shown.